Long before the sun began to shine, before planets took shape, the story of our solar system existed only as a theory, an attempt to explain how order could emerge from cosmic chaos. At the heart of this understanding lies the nebular hypothesis. It proposes a simple yet profound idea that our solar system was born from the collapse of a vast cloud of gas and dust, what astronomers call a nebula. Under the force of gravity, this cloud began to contract, spin, and flatten, eventually giving rise to the sun at its center and a surrounding disk from which planets would form. But this idea did not emerge overnight. In the 18th century, thinkers like Immanuel Kant and Pierre-Simon Laplace independently proposed that stars and planetary systems could originate from rotating clouds of material. Their insights formed the foundation of what would later become the nebular hypothesis. For centuries, the theory remained incomplete, lacking observational proof. It wasn't until the modern era, with advances in telescopes and the discovery of protoplanetary disks around young stars, that this model gained strong scientific support. What was once philosophical speculation became a cornerstone of astrophysics. Yet the nebula that formed our solar system was not pristine. It carried the chemical fingerprints of ancient stars. Long before our sun existed, earlier generations of massive stars lived and died across the galaxy. In their cores, nuclear fusion forged heavier elements, carbon, oxygen, iron, the very building blocks of planets and life. When these stars reached the ends of their lives, many exploded as supernovae, scattering enriched material into space. That debris mixed into vast interstellar clouds, seeding them with complexity. Our solar system formed from one such enriched region, meaning that every atom of rock, metal, and even life on Earth was shaped by stars that existed long before the sun. In this sense, the origin of the solar system is not just the story of a collapsing cloud, but the continuation of a much older cosmic cycle, a cycle of creation, destruction, and rebirth, written across billions of years and countless stars. Before the sun existed, there was a cloud. Not a small, isolated patch of gas, but part of a vast cosmic structure known as a giant molecular cloud. These are the coldest and densest regions of interstellar space, stretching across tens of light years, containing enough material to form thousands of stars. Within these clouds, structure emerges from turbulence. Filaments of gas twist and intersect, forming dense knots, regions where gravity begins to take hold. It is inside these knots that stars are born. The scale is immense. A single molecular cloud can span over 60 light years, yet its internal fragments, the seeds of future stars, are far smaller, collapsing into compact regions that will eventually ignite as stellar systems. But what truly defines these clouds is their composition. Nearly all of the mass is made of hydrogen, the simplest and most abundant element in the universe, along with helium. Together, they account for about 98% of the material. The remaining fraction, though small, is critical. Heavier elements like carbon, oxygen, silicon, and iron. These elements were not created here. They are the remnants of earlier stars, material forged in stellar cores and scattered across space by violent supernova explosions. Over time, this enriched matter mixed into molecular clouds, transforming them into chemically complex environments capable of forming planets, atmospheres, and eventually, life. And these clouds rarely exist in isolation. They're part of larger star-forming regions, stellar nurseries, where dozens, hundreds, or even thousands of stars are born together. The sun itself likely formed within such a cluster, surrounded by sibling stars, all emerging from the same cloud. In these crowded environments, radiation, shock waves, and gravity interact constantly, shaping the evolution of each forming system. The giant molecular cloud was not just the birthplace of the Sun. It was a dynamic, crowded, and ever-changing nursery, where the story of our solar system truly began. A giant molecular cloud can remain stable for millions of years, its internal pressure resisting gravity, its structure held in a delicate balance. But that balance does not last forever. Something must disturb it. One of the most powerful triggers comes from a nearby stellar death, a supernova. When a massive star explodes, it sends a shock wave racing through space at enormous speed. As this wave collides with a molecular cloud, it compresses the gas, forcing regions of the cloud beyond their stability limit. What was once a quiet, diffuse structure begins to fragment under pressure. Gravity takes over. These compressed regions collapse inward, forming dense cores, the first true seeds of future stars. There is evidence that this is not just theory, but history. Hidden within ancient meteorites are traces of short-lived radioactive isotopes, such as iron-60. These isotopes can only be formed in the extreme environments of massive stars and supernova explosions. Their presence in the early solar system tells us something critical. A supernova occurred nearby, just before our system began to form. The explosion didn't just enrich the cloud with heavy elements, it may have been the very event that triggered its collapse. As shock waves rippled through the cloud, pockets of gas and dust were compressed into ever smaller, denser regions. Over time, these regions lost their internal support and began to fall inward under their own gravity. This marked the beginning of gravitational collapse, the moment when a diffuse cloud transformed into a system in formation. From this point onward, the process became unstoppable. What began as a disturbance became the birth of a star.
As the collapse begins, the structure of the cloud changes rapidly. A once vast and diffuse region contracts into a smaller, denser fragment, what astronomers call the Presolar Nebula. This is no longer just part of a molecular cloud. It is a self-contained system, destined to become a star and its planets. But as the cloud collapses inward, something crucial happens. It begins to spin faster. This is the result of a fundamental physical principle known as the conservation of angular momentum. As the radius of the collapsing cloud decreases, its rotation must accelerate, just as a spinning figure skater rotates faster when pulling in their arms. What was once a slow, almost imperceptible motion becomes a rapidly rotating system. This rotation prevents material from falling directly into the center. Instead, the collapsing cloud begins to flatten, forming a dense, spinning structure. The central region continues to gather mass, while surrounding material spreads into a rotating envelope. At the same time, the internal conditions begin to intensify. As gravity pulls matter inward, particles collide more frequently. Energy builds, the temperature rises, the density increases dramatically toward the center of the nebula. This creates a clear gradient, a hot, dense core surrounded by cooler, more diffuse outer regions. Within roughly 100,000 years, this transformation reshapes the entire system, from a fragment of a cloud into a structured, rotating nebula with a defined center. The Presolar Nebula is now in place, a spinning, collapsing system carrying within it all the material that will become the Sun, the planets, and everything in between. What began as a triggered collapse has now become an organized cosmic engine preparing for the birth of a star.
At the center of the collapsing nebula, matter continues to fall inward. Gas and dust stream toward a single point, building mass, increasing pressure, and concentrating energy into an ever smaller volume. Over time, this growing core becomes the dominant structure within the system. This is the moment of emergence. A protostar is born. It is not yet a true star. Nuclear fusion has not begun, but the conditions are changing rapidly. As material continues to accumulate, the core becomes hotter and denser, glowing from the energy released by gravitational collapse. Around it, a rotating disk of gas and dust feeds the growing center, an active system of inflow and energy. Soon, the young sun enters what astronomers call the T-Tauri phase. In this stage, the protostar becomes highly dynamic and unstable. Powerful stellar winds begin to blow outward, and narrow jets of material are launched along its rotational axis at high speeds. These outflows carve through the surrounding nebula, clearing paths through the gas and shaping the environment around the forming star. Radiation intensifies. Magnetic fields become chaotic. The early sun is no longer quietly forming, it is actively interacting with its surroundings. Yet deep within its core, the most important transition is approaching. As pressure and temperature continue to rise, the conditions necessary for nuclear fusion draw closer. When that threshold is crossed, hydrogen atoms will begin to fuse into helium, releasing vast amounts of energy. That moment will mark the true birth of the sun. But for now, it remains a protostar, a growing, unstable, and powerful object at the heart of a forming system, on the verge of becoming a star. As the young sun gathers mass at the center, not all material can fall directly inward. Rotation changes everything. The collapsing cloud, already spinning faster due to the conservation of angular momentum, forces infalling gas and dust to spread outward. Instead of collapsing into a sphere, the system flattens, forming a vast rotating structure around the protostar. This is the protoplanetary disk, a thin, spinning disk of gas and dust extending hundreds of astronomical units into space. Within this disk, material is not evenly distributed. The inner regions, closer to the young sun, are dense and turbulent. Gas dominates the mass, while fine dust grains drift, collide, and begin to interact. Farther out, the disk becomes colder and more diffuse, with particles moving more slowly through the surrounding gas. But the most important feature of this disk is its temperature gradient. Near the center, temperatures soar, high enough to vaporize volatile substances like water, methane, and ammonia. Only metals and rocky materials can remain solid in these inner regions. Farther from the sun, temperatures drop. Beyond a critical boundary known as the frost line, ices can condense and remain stable. This allows solid particles to grow more efficiently, incorporating not just rock and metal, but frozen gases as well. This gradient divides the disk into distinct zones, each with its own chemistry, its own physics, and its own destiny. Gas and dust continue to circulate, collide, and settle within this rotating system, guided by gravity, pressure, and motion. The protoplanetary disk is no longer just a byproduct of star formation. It is the foundation of planetary formation, a structured environment where the first building blocks of worlds begin to take shape. Within the protoplanetary disk, not all regions are the same. Distance from the young sun defines everything. Closer to the center, temperatures are extreme. Radiation from the young star heats the inner disk to the point where volatile substances, water, methane, ammonia, cannot exist as solids. They evaporate, leaving behind only materials with high melting points. Here, metals and silicate rocks dominate. This region becomes the birthplace of solid, compact worlds, dense and relatively small. But farther from the Sun, conditions change dramatically. Temperature drops with distance, and beyond a critical boundary known as the frost line, volatile compounds can freeze and remain stable. In this colder zone, ice becomes a major component of solid matter, dramatically increasing the amount of material available for growth. This distinction reshapes the entire system. Inside the frost line, only a limited supply of heavy elements exists, restricting the size of forming bodies. Outside it, the addition of ice allows particles to accumulate more rapidly, forming larger cores capable of capturing surrounding gas. The result is a clear division. Rocky materials dominate the inner regions. Icy compounds and gas-rich matter dominate the outer regions. This process, chemical and physical differentiation, sets the blueprint for the entire solar system. It determines where terrestrial planets will form, where gas giants will emerge, and why the architecture of our planetary system is not random, but a direct consequence of temperature, distance, and the physics of matter in a young, evolving disk. Inside the protoplanetary disk, the smallest structures begin the largest transformation. Microscopic grains of dust, no larger than smoke particles, drift through the gas, carried by turbulence and orbital motion. At first, their interactions are gentle. When they collide, electrostatic forces allow them to stick together. Growth begins at the smallest scale. Over time, these grains form larger clumps, millimeter-sized, then centimeter-sized aggregates. As they grow, gravity begins to play a role. Collisions become more energetic, but also more effective, allowing matter to accumulate into increasingly solid bodies. This process is known as accretion, the gradual buildup of material through repeated collisions and merging. Eventually, these clusters reach a critical threshold. They become planetesimals, solid objects roughly 10 kilometers in size. At this scale, gravity dominates completely. These bodies no longer rely on simple sticking forces. They actively pull in surrounding material, accelerating their own growth. The transition is decisive. What began as drifting dust has now become the first true building blocks of planets. Within millions of years, countless planetesimals populate the disk, orbiting the young sun in vast numbers. They collide, merge, fragment, and reassemble, forming a dynamic, chaotic environment where larger structures begin to emerge. These are the seeds of worlds. From these early bodies, planets will form, not suddenly, but through continuous accumulation, interaction, and evolution. Accretion transforms simplicity into structure, turning dust into the foundations of entire planetary systems. The young solar system did not form in isolation. It was born within a crowded stellar nursery, surrounded by other newly formed stars, all emerging from the same giant molecular cloud. In this environment, gravity, radiation, and motion were constantly interacting. Nearby massive stars played a critical role. These stars emitted intense ultraviolet and X-ray radiation, powerful enough to heat and erode surrounding gas. Protoplanetary disks, like the one around the young sun, could be partially stripped or reshaped by this radiation, especially if located close to massive neighbors. But radiation was only one influence. The solar system was also part of a dynamic star cluster, where stars moved relative to one another. Gravitational interactions between neighboring stars could alter the structure of forming systems, stretching disks, redistributing material, and perturbing orbits. In some cases, stars may have passed relatively close to the young sun. These close encounters, though brief, could leave lasting asar. Their gravitational pull may have disturbed the outer regions of the solar system, shaping the orbits of distant objects and contributing to the unusual structure seen today in regions like the Kuiper Belt. Evidence suggests that the Sun was born among hundreds, perhaps thousands of sibling stars before gradually drifting away as the cluster dispersed over time. This early environment was not quiet or stable. It was energetic, crowded, and constantly evolving, a place where nearby stars influenced each other's formation and where even a passing encounter could reshape the architecture of an entire planetary system. The solar system as we know it today carries the imprint of that environment, a memory of its origins within a bustling stellar nursery. As the young sun continues to evolve, its influence begins to extend far beyond its core. What was once a system dominated by infalling material now enters a new phase, one of clearing and transformation. During its early life, the sun generates powerful outflows of charged particles, what we call solar wind. In this stage, these winds are far stronger than they are today, driven by intense magnetic activity and high energy output. These winds begin to push outward through the protoplanetary disk. Gas and fine dust, once abundant, are gradually swept away, blown into interstellar space, or dispersed into the surrounding environment. At the same time, radiation from the young sun heats the remaining gas, allowing it to escape more easily in a process known as photoevaporation. The disk begins to thin, gaps widen, the once dense environment of gas and dust starts to disappear. Over a period of just a few million years, most of the remaining material is cleared away. This marks a critical transition. Without gas, the rapid growth of planets, especially giant planets, comes to an end. The era of large-scale accretion slows dramatically. What remains are solid bodies, planetesimals, protoplanets, and the early forms of planets, now largely isolated from further material. The architecture of the solar system is no longer forming, it is stabilizing. This clearing phase effectively freezes the large-scale structure of the system. The positions, sizes, and compositions of planets are now mostly set, shaped by everything that came before. The nebula that once gave birth to the Sun and its planets is gone. In its place remains a young solar system, clearer, more defined, and ready to enter the next stage of its evolution. With the surrounding gas and dust dispersed, the solar system enters a quieter yet decisive phase of its evolution. At the center, the young sun undergoes its most important transformation. Deep within its core, temperatures and pressures become high enough to ignite sustained nuclear fusion. Hydrogen atoms begin to fuse into helium, releasing a steady torrent of energy. The sun stabilizes, balancing the inward pull of gravity with the outward pressure of radiation. This marks its entry into the main sequence, the long, stable phase that will last for billions of years. With this stability comes structure. The planets, formed through earlier collisions and accretion, settle into more defined orbits. The violent era of rapid growth gives way to gradual evolution. Gravitational interactions continue, but the overall architecture of the solar system, its layered arrangement of inner rocky planets and outer gas giants, becomes established. At the same time, the solar system begins to drift away from its birthplace. The original star cluster, once crowded with sibling stars, slowly disperses. Over tens to hundreds of millions of years, gravitational interactions between stars cause the cluster to break apart. The Sun, along with its newly formed planetary system, is released into the wider galaxy. From that point on, the solar system travels alone, orbiting the center of the Milky Way, completing one revolution every few 100 million years. What began in a dense stellar nursery has now become an independent system, stable, structured, self-contained. The foundations are set. The Sun shines steadily at the center, and around it, the planets continue their motion, following paths shaped by the earliest moments of their formation. The chaos of birth has ended. What remains is a system ready to evolve over billions of years, carrying within it the conditions that will one day give rise to worlds, atmospheres, and life.